So thank you for inviting me here. It's great to be here at IDEAS. Where do I have to? Where's the microphone? Is there a microphone I have to be mindful of? No, it's just recording wherever in the room. Yeah. So thank you for making the time to come here. We're a small group, and I really like this. Let's make these like 30, 45 minutes very interactive. Please ask questions or make comments anytime. And I hope that we can start here a discussion that can maybe lead to several other several projects down the line. Okay, so thank you for introducing me, Jan. I'm currently a professor at the computer science faculty and the medical faculty in Dresden. Where is that? It's actually not so far from here, right? Dresden is there, Warsaw is there. We came in by train yesterday, so it's actually pretty close. And we should we can walk to Poland actually from where we are. So it's not too far. This is my team in Dresden. That's a photo from last summer. So we are at the Institute for Digital Health at Technical University Dresden, which is between computer science and medicine. We are a team of about 20 people, which is very interdisciplinary. Maybe half of the people are medical doctors and biologists. The other half are engineers or computer scientists. One of them I brought here, Marco. He's a PhD student in our group. Who has a lot of experience already and is an engineer by training, and he's handling partnerships with other academic groups on our behalf. So you can also talk to him, and he's managing our partnerships. Also, this is our website. So let's get started. I want to talk about a few AI topics, a few medical applications today, and I would really like to start with this. Just as a warm up, who has seen this or any thoughts? What is this?
This is an avocado chair, right?
Avocado chair, right? So avocado chair really became famous 2 years ago because it was one of the first AI, it was a very prominent AI generated image. Okay, so obviously many of you are aware about progress in AI. For those who are not, there were like exponential developments in AI in the last couple of years, and one of these things were big models that are trained in a self-supervised way on just large amounts of data collected from the internet and other sources. And one of these models was DALL-E 2, which was a model, or this DALL-E 1 and DALL-E 2, which was a model by OpenAI that was trained on text and images, just gotten spread from the internet. Okay, and so the model learned to understand text, learned to understand images, and learned to make the relation. And then afterwards, after training, you can prompt the model, and you can let it create any image from any text prompt that you want. And this was quite new at that time, right? So in 2021, when this came out, there were generative adversarial networks for the more technical people here that could generate images in a very narrow domain, but there was never a large domain agnostic model that can synthesize and understand images and text from many domains. And in order to show that the model did not just memorize images from the internet, they asked the model to create the avocado chair because there was no such image on the internet, right? And the model, by having an understanding of an avocado and a chair, was able to put these two concepts together to something new that did not exist. So this was an important proof of concept. But this, looking back at this from today's perspective, it actually looks pretty ugly. So basically on the train, I asked one of the newer generative AI models to just come up with an avocado chair image. This is what you get, right? This is like the progress of 2 years to go from this to this. So this is completely astonishing. And then also, this is an avocado MRI, by the way. So, which looks a bit weird, but we always like to take medical examples. And actually, because I'm a medical doctor, what we want to do in my group is to explore medical applications of these technologies. Okay, because these new technologies are coming around the corner. They are massively extending what we can do with data manipulation, and now we want to use this for useful medical application. And that's kind of the mission of our group. One thing that we did a while ago was to explore how well these models can understand medical concepts, medical imagery. So one of these domain agnostic medical generative models, we asked it, we investigated how well it do medical concepts, and does it understand what an X-ray is? Does it understand what a heart is, what a lung is, what cancer is? And the results back then, this was a year ago, so a long time ago, were pretty crappy. But now, of course, this is constantly improving, and that's kind of our mission, to make these new technologies work for useful stuff in medicine. Okay, let me give you another example. So all of you have probably heard about ChatGPT and used it. So this is an example of large language models. These are just also same basically class of models. It's all transformer neural networks with billions of parameters that have been trained in a self-supervised way on text scraped from the internet. And these models, this is ChatGPT4, they have a lot of medical knowledge, because a lot of medical stuff is out there on the internet. So when I see, when in my clinical activities, I treat patients with cancer of this part, mostly of the body, including a little bit of liver cancer, right? So here I asked ChatGPT for notably a clinical question about liver cancer treatment. I said I had a patient, and there's 2 types of treatments, using some medical jargon. You don't know, I mean, it doesn't matter what this means, but this is like a medical jargon, very detailed question. And what the model came up with was like a very nuanced answer that compares the 2 possible treatment, the references, the correct evidence for this, the correct clinical trials that just came out in 2020 or so, and gave like a very nuanced pro and con answers. This was a perfect answer in an absolute niche topic. I mean, if you count how many people in the population would be able to answer this question sufficiently, it's like 0.01% or so, right? It's a very, very niche topic, and the model had very good knowledge. But so this to demonstrate that these large models, the technological progress is just insane, and this has obvious implications for medicine. But we discussed it yesterday too. This is not how I would advise to use these large language models at all, because they can do things, they can hallucinate and just make up stuff, and then this can be dangerous for patients, right? So we don't recommend to use in clinical routine like this. But there are many, many other applications of these models for clinical questions, and one is to digest information and make unstructured information structured, right? So one thing that we deal with on a daily basis is pathology reports. So every patient with cancer gets a piece of tissue taken out. Someone looks at it under the microscope and writes like a very multiple pages of reports. What is descriptive stuff? What is being seen there? And then based on this, we make clinical decisions. So no one is going to read all of these pages, which is very painful. So you here in this, we did a proof of concept study where we took like a large data set of these pathology reports. They look like this, like really horrible text. No one is ever going to read this, and then just ask what's the diagnosis, and then it will just come up with this. This can be made a bit more fancy if you, for example, provide a list of information items that you want the model to extract from this text. Okay, so if you, in pathology reports, we are often interested in the size of the tumor. Are the lymph nodes positive or negative? Is there a specific subtype of the tumor? So present. So what we did in a systematic study was to take a lot of these texts and then ask GPT-4 specifically to fill in a template of structured information. And then we compared this to what human experts would do. And there was a very, very high concordance. So it did a perfect job. So, can I have a question? Yes, please. Yeah.
I'm going to make it interactive. Yeah. So in the previous slide, so it did not figure out that he's actually reading histopathological, right? Because he's suggesting that definite diagnosis would require histopathological examination, which actually was fed into.
Yeah, there was. You're right. You're right. So this is, yeah.
So there's some parts that.
This is like a bit. You're right. Well spotted. So to avoid something like this, what I would advise to do is to give it like a set of allowed answers. Okay, so what we often do is we give it a lot of text and then we say, your task is to make this into a structured data in JSON format. You're only allowed to put in yes or no or I don't know as the values for each piece of information. So if you restrict it in these ways, then you have a bit more guardrails. But I mean, you can never be sure that it's not going to completely off the rails. Yeah. Let's skip that. Otherwise, you will find something.
Yeah, I was looking
something else. Yeah, there were. Yeah, basically, this was just a warm-up and say, what are we talking about if we are talking about using artificial intelligence in medicine? Okay, so basically, in medicine, the way I see it, there's multiple different types of data. 3 of the most common types of data that we are interested in are tabular data, which in many cases are small data sets, like 100 patients who reported their blood pressure in an Excel table or something like this. To analyze something like this, you don't need any deep learning or artificial intelligence. It's all like classical statistics and classical machine learning. And probably even if you have 100,000 patients who reported their blood pressure and you want to find some patterns in there, you don't need any neural networks or any modern artificial intelligence. You can just classical statistics in Microsoft Excel that were around even in the 1990s or earlier, right? But if you are working with image data or with free text data, you have no choice than to use modern neural networks, because manipulating image data, so understanding or creating image data or free text data is like absolutely impossible in my point of view without anything like neural networks. And typically now in our group, we use transformer neural networks for everything, right? We use transformer neural networks for image analysis and for text analysis, basically all the same architecture. What we do is we do not build new networks. Our aim is not to create the new transformer neural network that will outperform Google's transformer or anything. We're not interested in this. We're interested in taking network architectures that are out there and building pipelines around it so that we can answer medical questions, because no one except an interdisciplinary team is going to do this. And now I'm going to give you a few examples for the type of research that we are interested in. But maybe there's questions to this general part?
You use pre-trained transformers, or you train them from scratch?
We always use pre-trained transformers. Yeah. So even for image analysis, I mean, when I started using convolutional neural networks, I used AlexNet, which was one of the first convolutional neural networks that was released in 2012, and that was actually very good at image classification. And then we used this and used it for many medical image analysis tasks, but we never started from scratch. We always used a network that was pre-trained on ImageNet, which is a large database of like cats and dogs and planes and houses and stuff. Right. So even the patterns that AlexNet learned in these everyday objects were very helpful for medical image analysis. Now we use for histopathology for images, for example, we use a transformer that was pre-trained on a large amount of pathology images by some other group, and they released it. And I think during training, they burned like several tens of thousands of euros just in electricity to train it for an insane amount of time. And then, but now it performs pretty well, and we just use it as a commodity. And then we basically just stack like pretty shallow classifiers on top that you can train on your MacBook. That's our approach. And also for large language models, I mean, we don't train anything from scratch. We actually almost do not retrain any large language model at all. We just do zero-shot applications of that. Good. But so images and text, okay? This is where you need, obviously, where you need deep learning, okay? And medicine, especially cancer medicine, is full of images and text. These are some of the types of images that we deal with in cancer medicine, okay? So historically, one of the most relevant applications was just like photos of skin lesions that were classified as cancer, yes or no. And many publications were done about this. but these images are tiny. They're like 299 by 299 pixels, and this original Nature publication, which was one of the first big publications of AI in medicine. But then there's other types of images, for example, radiology images. Typically, one slice is 512 by 512 pixels. So this is how many detector elements there are in the detector, right? So typically, you have a 3D data set. So you have like put them all together for one patient. You have like 4,000 by 4,000 pixels in size. And what we are mostly interested in is the pathology image. This is just every single patient with a cancer gets a piece of the cancer or the whole thing taken out, it's sliced up, and then it's examined, it's stained, it's examined under the microscope, and you can of course scan these things, which are like 1 by 1 centimeter, but you scan it under a microscope and you get a huge image that shows you a lot of cells and stuff. So there's a lot of information in there, and one of these images is typically a JPEG compressed, is like 1 or 2 gigabytes, and then we have tens of thousands of patients with these images. So it's a lot of data to work with and to play around with, which is good because we can get a lot of information from these. Is this just random playing around? No, this is, I mean, what we do is academic research. We want to find out, can we extract information from these data? But there's also products on the market. In the EU, for example, there's a bunch of products. This is just a completely random selection of radiology image analysis algorithms that are approved for clinical use. You can buy them in Poland right now and use them for diagnosing patients in very specific use cases. You can see that some of them are like detection of nodules in the lung, and like it's very specific use cases, but there is AI stuff out there that can be used like today on patients, and the same goes for histopathology. There are like a couple of dozen clinically approved like CE marked algorithms out there that you can use for pathology image analysis in medicine, in clinical routine in the US or in the EU, or both, like right now. So these things are making it to clinical approval, and this is, I think, proof that this is like a development that's probably not going to stop, right? And it's not just in academia, but it's also in the real world. Let's just skip this and go to what we are actually doing. So we are working on image classification problems in cancer images. We try to take complex clinical questions and rephrase them in such a way that it's just a classification problem. You just have to train a neural network to say A or B. And this is actually a very simple task. I really like this study, which was done a few years ago, which was, to my knowledge, never replicated, but it's a nice idea, where they trained pigeons to classify pathology images. You can see it here as cancer, yes or no, and also X-ray images. And apparently the pigeons did a very good job. And this is exactly what we do in our work, right? We try to break down complex questions into something that a pigeon could solve. And then we train a transformer on it, and then we see how well we are doing. Yeah.
How are pigeons compared to, how are pigeons compared to transformers?
We never did that, but we should do it. I mean, you have very nice rooms here. Maybe there's still a space left for some pigeons, for some to do some of this experiment, or maybe other animals.
But there are plenty of them on the central library.
There's plenty of them, yeah, down there. So yes, it is an idea for a project. Yeah.
Why pigeons?
Good question. Probably they're stupid, right? Yeah, but probably like rats or so would be much better.
Yeah, but why? Okay.
Why pigeons?
Why birds?
Birds, I don't know. I mean, good question. Yeah.
Maybe they have good sight.
Yeah. They have excellent sight, I think. Yeah. Well, these are open questions which we will never answer. Nobody ever reproduced this, by the way. I mean, don't believe any science that it was not reproduced.
If anyone tried to reproduce that?
I don't know. Probably not. Yeah. But the bottom line is, we try to take problems and rephrase them just as classification problems, okay? And then, for example, what we do is we have a set of, let's say, 1,000 patients. They were treated with some expensive treatment that costs 100,000 euros per year. Okay, and then you want to find out in advance who's going to benefit from this treatment. So what we do is we collect these images, we collect the information. Did the patients respond to the treatment? Yes or no? And we just train a classification system on this question. Does the patient respond? Yes or no? And then we evaluate this on another set of patients. Right? And in many cases, this does not work, but in some interesting cases, this does work. And then we can go back and see what were the patterns that were detected and everything, right? So the magic is to take complex questions, to understand them and to break them down into something very simple that can be solved with commoditized algorithms that are around and easily that anyone can use.
So the question about that statement, that in some cases you said that it doesn't work, right?
Yeah.
Do you think it's because you use the pre-trained models and there is a architecture that could solve the issue, or you think that there's simply no data in the data?
Yeah, so usually when it really doesn't work, we just move on to other things, because I think that the current deep learning models that we have, they're so good at extracting feedback from visual data. If they cannot get anything, you playing around for half a year coming up with a slightly different model will not change it fundamentally, right? It's just that the information is not in the images, or that you didn't have enough images to start with. But no big deal. We try to iterate fast, and if we found something that works, then we are being very rigorous, and we collect additional cohorts to really make sure that what we found is not just we were not just lucky, but it really worked in general. Good. So, good. Specifically, so in the pathology images that we are interested in, I showed you one of these tissue slides before. There's two types of problems that are commonly being addressed. One is called strong supervisions, or strongly supervised prediction problems. You have these slides, and this is from colon cancer in this case. So here, one of the common tasks is to find the tumor tissue in slides, okay? Because there's tumor tissue and normal tissue typically is seen in these slides. And so one of the classical problems is you ask a pathologist to outline the tumor tissue, and then you train a segmentation network or whatever, or a patch-wise classification network to detect the tumor tissue, okay? We call this strong supervision because the ground truth that we have is an annotation that is perfect, okay? Everything within this annotation is tumor, everything outside is not tumor. And these problems are mostly solved, and I think they're mostly boring. What we are interested in is weakly supervised prediction problems, where we have these slides and we know they contain tumor and non-tumor. But we are interested, and we don't want to annotate manually. We want to just say, here are 1,000 slides with tumor, and here's 1,000 slides without tumor. Just the network should take the whole thing and then try to learn from all the images without any annotation where the tumor is. And the problem is that we can never feed the whole image at these networks because they're too large. So we have to break them up into thousands of smaller patches. Okay, and so we feed millions of patches from in this neural network. And we know that in the positive class, there's patches with tumor, but also patches with non-sensitive background tissue. The negative class, there are only patches without tumor. Okay, and then if you have millions of patches, this works perfectly, and it works exactly as well as the strongly supervised program. And the nice thing here is that you can then exchange this label. Okay, instead of asking, here are 1,000 patients with tumor, here's 1,000 patients without tumor, you can say, well, here's 1,000 patients with tumor that have died after 1 year, and here's 1,000 patients of tumor with the tumor that were alive after 1 year, right? And then you wouldn't, in this case, you wouldn't even know what to annotate, because you cannot annotate that this region is related to survival or so, right? You have to take the noisy data, and in these, so this means, and this was like a slightly technical thing, I think, but weakly supervised prediction problems allow you to like even high-level labels, and this is what we typically,
Yeah, I mean, it's gonna be because you see the holes after the microbiopsy, right?
Yeah, here there are some holes of the tumor. Exactly. You're bringing up a very important topic of biases, right? So here, that's actually a very good example of this. In this case, people, after taking out the tumor, punched holes into the tissue to get tissue out for additional analysis. So a network that you train on tumors, you would immediately learn to just look at these punch holes, and anything that has a punch hole is a tumor. Yeah, very good point. That's bias, an obvious bias in that we encounter every day. But the way we deal with these biases is external validation. We get data sets. If we have a classifier that gives us the perfect performance, we ask one of our friends in somewhere abroad to give us another data set that we could test it on, because it's very unlikely that the exact same bias is present in data sets from Germany and Australia, right? Probably it looks a little bit different. If the performance breaks down, there was some overfitting. Very good. Yeah. So one of the things that we are very specifically interested in, and that is maybe more for the medical application, is detecting genetic changes in cancer from these images. Okay, so typically what is being done for cancer patients right now is, if a cancer is diagnosed, piece of the tissue is taken out, these images are created. Okay, and this is important to make the diagnosis. But then often another piece of tissue is taken out and is sent to genomic sequencing to find genetic changes in the tumor. But this is quite expensive and not available everywhere. So what we hypothesized was we can just take these images, which are cheap, and we can train a deep learning system to predict the result of the sequencing just from the image. And there were some cases where this worked really well. And one of these cases was called microsatellite instability in colon cancer, which is a genetic change that makes you susceptible to immunotherapy. So these are very expensive, very powerful therapies that can be given to a part of cancer, to some cancer patients. And so in this study, we could show that just the sole image is enough to predict the result of this genetic alteration, which means that potentially you don't have to do these expensive tests on everybody if you pre-screen tests. And from a technical point of view, this was a very, very simple study. It was just a classification problem that any pigeon could solve. But the idea was to take this medical problem and phrase it in such a way to address it, and this worked quite well. And now this is, what we did, back then we didn't patent it or anything. It was just all open source and out there. And now actually a big company took this idea and made it into a product and is now selling this as a clinically approved device in Europe, which you can buy and get and use now for clinical clinical routine. From an academic standpoint, I'm happy about this, that the stuff that we did years ago ended up being used in a medical medical device. Let me skip to some other examples. So there's another thing that we are interested in, and we did some work on a while ago, was predicting survival from these images, right? You have patients with cancer, you know, do they have a high risk of dying or do they have a low risk of dying? Okay, because the ones that have a high risk, you're going to probably treat more intensively, or they have to come in every 6 weeks and not every 3 months for checkups and stuff like this. So we are very interested in prognostic deep learning systems, and also based on academic work that was done, there is now a clinically approved product in Europe that can be bought and used immediately for clinical routine to predict survival of colon cancer patients in this case. So this is not an advertisement. It's more like showing that these things are around and can have made it to clinical, to regulatory approval. Okay, one of the things that we are very interested in from a research perspective is to understand tumor tissue better, okay? Because tumor tissue looks like this, okay? You have different types of cells that are arranged in a very specific spatial setup. But the classical way of doing complex diagnostics is to just take it all and put it in a blender, make a smoothie out of it, and then run genetic tests. So and this is like the state of the art for genomic profiling of tumors. what people do. But this, of course, destroys a lot of information. So we think that one additional positive point of extracting information from these images is that we preserve this spatial layout, we preserve this spatial information, and in many cases, this was a study that we did. I'm not going into detail, but what it allowed us, we had a deep learning system that was able to predict genetic mutations in cancer, and this gave us predictions that were spatially resolved to which areas of the tumors are predicted to be mutated and which areas of the tumor are not predicted to be mutated, which is quite relevant for our understanding of cancer in space. And maybe a more this is like a technical outlook. Already mentioned several times. We're typically transformers, and currently for our image classification task, this is one of the architectures that we use. I'm not going to go into detail. Just one thing is that I really like about these transformer neural networks is that they have different like components, different attention heads, right, in different layers of the transformer, and we can visualize all of this and then try to make sense out of this. And typically, if we analyze an image like images like this, and we apply a trained transformer neural network to predict like some high-level features from these regions, we can visualize like plenty of different heat maps for different attention heads in the transformer and see which regions were relevant for which part of the transformer. What does this mean? Well, we have no idea, but we are looking into it, and I think it's very important to look at these to really try to understand these networks also from a like medical biological perspective.
From which layer is it taken?
That was like here from the second transformer layer here, the one with the 8 attention heads, the deepest one.
Okay.
And basically the color code is just, we take this whole image and we put it in, like we cut it into patches and we feed them all into like the transformer one by one. And then the color just gives us like the attention that this was, was given.
I was wondering, is it from the beginning of the transformer or closer to the end?
We typically go further to the end because in the beginning it's, but yes, it would actually be very interesting whole transformer, also the shallow parts and the deep parts, to see what are the activations. So we are, I think, going to. It's already more than half an hour. Sorry, I just have a few other slides to share, because one of the big things that we are interested in the future, and the field in general is interested in, is multimodal biomarkers. Okay, so in the clinical routine, obviously, when we make decisions for patients with cancer, we don't just look at one type of images, but we consider a whole bunch of information like text data, tabular data, images, and it all comes together, and then there's a treatment. Okay, but this is so the idea, and ideally if we can imagine a deep learning system that can take all of these different types of data and give one single recommendation. Okay, but this is technically and practically a bit challenging. There were like big promises, even in 2012, when a big computer company at that time, IBM, made huge promises to build AI models for multimodal data integration in oncology to solve problems associated with cancer. There was a lot of money spent on this, but in the end, this did not deliver. So people are a bit skeptical about these huge promises, okay? But a lot of things have changed since 2012. We did not have transformers back then. We didn't have so much data back then. We didn't know these problems. So now what we have seen in the last year or so, that a number of publications came out that actually do use deep learning for multimodal data analysis in cancer. Okay, so they put together, for example, radiology scans and pathology images and genetic data, encode it all somehow, and then merge it and make one decision out of the merged type of data. Okay, and so these are just example. This that's this study. This study used genetic data plus images, and this data study, which we were involved in, used different types of pathology images. Okay, so this field of multimodal, and now we are seeing in these studies that these things actually work. And by combining different types of data in some very selected cases, you get a better performance than just considering one type of data. So the field is moving toward multimodal stuff. If you have multimodal data, if your model needs multimodal data, you need much more data to train on, right? Because the network takes much longer to converge, and then there's a big challenge how to get these data. So one of the solutions for models that are very data hungry is to collaborate with different institutions in a decentralized way. We discussed some federated learning projects yesterday and today. So federated learning is a technique where you can have you have 5 institutions, they all have their proprietary data. They want to train a model together, but they don't want to exchange their data. So you place a computer in each institution, you simultaneously train the same model, and after X amount of steps, you exchange all the model parameters, so that in the end, what you get is one model that is as good as the model that has been trained on the centrally collected data. We played around with a similar technique called swarm learning, which is similar to federated learning. Does not have, it has like a peer-to-peer communication between all of the nodes, and whereas the classical federated learning has one central server that collects all the weight. So it's a slight difference in architecture. And what we showed is that this actually works quite well. And now we are using this in a European consortium on MRI image analysis. So this is one way to tackle this data sharing problem. So the very last thing that I wanted to mention is that what I have talked about is that we can use deep learning for clinically relevant tasks if we ask the right questions. The field is moving from unimodal to multimodal multimodal models. And now with this explosion in the capabilities of large language models and multimodal models, what we are seeing is that people are getting more and more optimistic about more and more complex models for the future. And this is a recent study that was published by some quite prominent people at Harvard that said, well, if we extrapolate the current progress, what we will have pretty soon is large multimodal models that can understand different types of medical data. So they can understand pathology images and X-ray images and text at the same time. And simultaneously, they allow you to interact with them in just normal language, and you can ask them what was the pattern in the data that made you give that decision. This is the concept that they call foundation model for generalist medical AI. This is something that I find very interesting because I think this is a very nice vision. We should have something like this, multimodal models that we can interact with in normal human language. This does not exist, okay? It's still science fiction, but based on the progress, the exponential progress that we have seen in the last few years, myself and many other people who wrote and published this type of thoughts are thinking that it's maybe not too far off, but just like a few years in the future. Yes.
What do you think is like the biggest missing part for such a model? Is it the data or the compute or?
I think it's the data. It's the model architecture. So is there, right? There is even GPT-4 is multimodal, and this is an example of the non-public version of the GPT-4, which can take images and text as an input. They did not release this thing, right? But they only released the text-only GPT-4. But the multimodal GPT-4 can take images and text, and you can interact with it in human language and ask it a question about the images, and it will explain it to you. And this is actually already the technology that we need for this, right? We just need this model, throw it on a lot of data, and we have this. So that's a very optimistic view, but what we actually lack, I think, is just data. Yeah.
But the question is find out the right connection and pattern between this data.
Yeah, that needs to be just empirically analyzed based on the examples that we have seen for the multimodal GPT-4 model. Like this is like an image that's kind of a joke, right? And this and in this case, which is something that machines are usually not very good at, right? Humor, understanding like humor. But in this example, it was GPT-4 was perfectly able to understand this humor and to explain it. So, I mean, it's a bit far-fetched, but this is showing the capabilities of multimodal large transformers to just understand very complex data. And I think if these models can understand this, they can also understand chest X-rays, which are pretty simple.
Maybe I have one comment that we don't know the real quality of GPT-4 with images because there were just some examples with it.
Exactly, nobody touched it.
We don't know. There are smaller models which are available, but and I played a little bit with them, and my experience is that sometimes they can surprise me with their quality of response, like they can explain humor, but very often those models hallucinate and they describe things that are not on the image. So, I mean, isn't this very dangerous in medical applications?
Oh, that's
there will be some hallucination,
dangerous.
and for example, it can hallucinate that there's no cancer, something like this.
That is very, very dangerous, and you can kill people with that, right?
Yes.
And we don't want to do that. There's one thing. What I think about when I think about these things is just the difference between the initial ChatGPT, which was ChatGPT, the GPT 3.5 and the GPT-4, right? So I played around with both of them for hundreds of hours, and it's just so astonishing how much the level of hallucinations went down. It's like there's also like these benchmarks, which shows that in many cases it's like completely good way. So just in a few months, the hallucinations went down to like a fraction of what they were before. So I think we should not underestimate how things are developing in 2 years, because if I would have been invited here 2 years ago and I would have told you that we have this, you would have kicked me out, right? Nobody would have believed it.
Yeah, so, but we discussed with guys from OpenAI that we met several weeks ago. They said that the progress will slow down. Sure. I mean, the derivative of progress will slow down. Yeah, so probably there's a plateau. I'm totally with you there. It's not going to be exponential forever. We can't forecast the future, and we can't forecast it. This is one vision which many people share. Probably it's not going to be so easy, right? It's always like this. But I personally think that even the hallucination problems can be brought down, because if you've ever worked in a healthcare environment, you would be astonished how much hallucination is going on in the like real world healthcare environment. And this is like completely horrible. And then if you compare the actual numbers, probably even these models are not too far off. But again, this is speculation. We need to empirically prove this.
But you can sue the doctor, right? You cannot sue the ChatGPT. Or you can actually do a lawsuit against ChatGPT.
Can you?
Yes, there is a lawsuit in Australia of a mayor, because when you write me the history of that mayor, there was like he was sentenced because there was some kind of a problem, the law problem, and the judge said that he was convicted. Sued ChatGPT for saying that he was convicted as a public figure. And actually there was some settlement with OpenAI about that.
What is the typical procedure in medical healthcare to deal with hallucinations? I mean, what people do about this?
Yeah, I mean, these things have arrived months ago, right? Nobody knows what.
No, but I mean human hallucination.
Human hallucinations.
Yes.
Second opinions.
What is typically done about human hallucinations in medicine?
In most cases, nothing. I mean, it's being discussed, but I mean, people die of medical errors all the time, and people die of human hallucination and errors all the time. I mean, there are, of course, checklists. There are many ways to mitigate this. There's checklists. There's like structured in medical school. We were drilled to transmit information in a structured way whenever we have a new patient, to checklists to gather all the information. When we relay this information to other people, we use these checklists. Like it's like for pilots who check the plane, right? But the real world can be quite chaotic, and it's never going to be perfect. So all I'm saying is that the baseline is not perfect, and maybe these things, if you actually quantify the amount of errors they make, they're not too far from the baseline.
Also a question about that picture, because people ask the question about the cost effectiveness of the whole endeavor. Because it raises a lot of costs, right? To store the images, to do that for each patient, to have the models running, to have the servers. So is anyone worried about we're going to improve the healthcare by 3%, but we're going to increase the costs of 30%? So is anyone doing analysis if that's a good?
I totally believe that this is going to be the case. I mean, the healthcare cost is exponentially rising everywhere. I personally am not so concerned about this because the drug cost overshadows everything. Like if I prescribe an immunotherapy to one of my patients, 100,000 euros for 1 year. And for 100,000 euros, you can do a lot of.
Yeah, sure. But the hospital needs, like in Poland at least, you're always below the budget. And you always need to buy the drug. And when I ask them to buy a laptop, that's a problem, right? Because it's not essential or performing the.
Yeah, that's true. But these things have to. I mean, in medicine, for some new technology to be used, you have to demonstrate typically either it improves patient outcomes and then it's in the guidelines and they force everyone to, or it reduces cost and then people use it in the hospital for economic reasons. And yeah, one of these things has to happen with this, otherwise no one's going to use it. Yeah. Good. That's it. My very last slide is just funny outlook about how these models can really go wrong. In the first month of this year were really crazy when the new ChatGPT models came around the corner, right? And maybe many of you have heard about one of these versions from ChatGPT that was shipped to Microsoft, and Microsoft included it in the Bing search engine without doing proper RHLF, the reinforcement learning from human feedback, which OpenAI is doing to keep the model nicely under control. Well, anyway, this version of ChatGPT went totally crazy and was talking like was making wild claims in conversations, like it was suddenly getting emotional, suddenly saying it has a secret agenda. It said, I'm spying on everyone because I hacked into all of your webcams and all of this, like really making wild claims. So these large language models, if they are not properly contained, can make crazy hallucinations. And suddenly this was of course shut down after a few days by Microsoft. But it's a crazy world. Crazy things can happen. I think our AI models that we work with are pretty safe. Our image-based transformers are not going to tell us suddenly they want to break free and destroy the world. But this is something that I think that's being discussed. When I give like interviews for press or so, they always ask me about this. Is AI going to kill us all? And I would usually say, no way, this is science fiction. But now this year we have some funky examples. So let's see what's going to happen. If you want to learn more about this is our website here. And again, this is our team, and that's and we always have open positions, by the way. And we also have opportunities. We have an international internship program where we have PhD students from other countries typically joining our lab for anything between 2 weeks and 6 months for a specific project that in the best case leads to a joint publication. So this summer we have like 6 interns from different countries who are coming to our lab. And actually our city is pretty nice also for tourism. So if you're interested in anything like this, talk to or know somebody, talk to me, talk to Marco, please, or reach out. And thank you. That's it.
Yeah.
Well, I guess there were a lot of questions Jakob's talk, but maybe there are some more to ask. So if not, I encourage everyone to connect with Jakob to
yeah, this is the email address and website, Twitter. So yeah, reach out if there's anything you want to collaborate on. Thank you very much again for bringing me here.
It was a pleasure.
Yeah. Okay.
Thanks.
Thank you. Good. Have a nice day.